So we're talking about limits today, and I'm going to approach this as if I didn't mention anything about it on Monday. Okay, so that's good for the 2 students that missed class Monday. How many are here today? 5, 10, 15, 24, all of us. Wonderful. Noel, your camera's off. And I guess what happens if you get a call or a text, your camera will turn off. And this is something important to think about on test day. You're going to make sure you put in do not disturb mode for that 1 hour and 20 minutes when you take your first test, chapter 2 test. Just so that the camera never turns off again. Thank you. And so we're talking about limits, and we started with an informal definition, and then we're going to look at a bunch of ways that we find limits, and then we're going to bring back in that formal definition and show a connection with everything. So limits, I like this informal definition, right? And I like to say that a limit is a predictable height of a function. Predictable height or value of a function. And so what am I talking about there? An x value or a y value? A y value, right? So we're looking at the limit as like x goes to c of f of x equals L, right? So we're just looking at some function, right? As x goes to c, I should be able to find the height L. In fact, I should be able to find it without actually getting to c. I should be able to predict that value of the function or that height without actually getting there. So like meaning, imagine me walking up this hill and my shadow, right? The shadow on the ground is moving towards C, right? I'm moving up the hill, the shadow's moving towards C. I should be able to predict what height I'm going to get to, right? In fact, even if I do it, walk the other way, right? If I'm walking downhill here, right? So this is C from the left, this is C from the right. So I should be able to approach that value of x from the left or the right and make a prediction about L. About what height am I going to get to, right? And we kind of saw that when I talked about that secant tangent problem. Right? If I'm interested in the slope at one point, right? This is my tangent line. My tangent line is a line that's connected to one point. Now I don't know how to calculate that slope yet, right? And that's what the first part of this course is about. But if I can pick some other point on the curve and then move that other point closer, right? You can see that my secant lines are getting the slope closer and closer to the slope of the tangent line. Is that clear from my picture there? I'm a little bit messy with it, but I know I drew it Monday as well. So as I move my points closer and closer, the secant lines are becoming the tangent line or getting closer to them. And that's again me making a prediction. What's going to happen to this? Where are the slopes of the secant lines changing to, right? And you're going to see that very easily today when I do something called a numeric limit. How we doing here? We okay? Nice. Thank you. Thank you.
So when you rate the limit of x as it approaches c, that's just the general limit approaching from the right or the left.
Exactly. And you'll see when I do a couple today, I'll say the limit as x goes to c of f of x is L is equivalent to, or if and only if, the limit as x goes to c from the left is L, and the limit as x goes to c from the right is L. If I get a match left and right, I got a limit. And so we're going to do limits three ways today. Graphically, very easy. Numerically, very easy. Also never on a test because it's too easy. And then algebraically, those are the ones we want. So when we do limits on our first exam, you're going to find them algebraically, but then you want to verify either graphically or numerically. And we'll talk about this quite a bit. So this is the function y equals absolute value of x over x. And so when x is positive, I'm going to get a height of 1. When x is negative, I'm going to get a height of negative 1, right? Because x over x is 1, right? I can't divide by 0, so it doesn't exist at 0. But so if I'm interested in here, the limit as x goes to 0, right, of y, this one does not exist, right? Because on the right, I'm walking at a height of 1 all the time towards 0. And on the left, I'm walking at a height of -1 all the time all the way to x is 0, right? So you can see, am I going to meet at the same height? No, right? So I guess the trickiest part about this is, well, when do I need to think about left and right, and when don't I? And for most of the time, when it's algebraically, you don't have to think. The algebra takes care of the left and right itself. The numeric will take care of the left and right, but on that one, you'll always do a left and right. And then the graphical will be obvious. If the two heights don't match up, left and right, there's no limit, right? You can't predict because you don't know which side you're on, right? Does that make sense? You can't tell which side you're on if I just say it's a function. But this is coming up. So if I don't know if Jesse, that answered your question there, or yeah, okay, thank you. So we want to look at the three types of limits that we're going to be talking about, and that's homework 1, homework 2, and homework 3. Algebraic, graphical, numerical, right? So algebraic, and this is homework 1, graphical, homework 2, and numerical. Homework 3. I think I have them in order. It doesn't matter. We're going to be able to do all of them after today's lesson. Okay. But the only one I'm going to ask you on the test is algebraic. But I like having these three processes because each of them could verify the other. And that's something that you're going to do on your test. You're going to solve it algebraically, and then you're going to verify that you got it right, either by looking at the graph or by doing a table. And I'll show you how to do both of those today. So, before I do this, let me do one of these, okay? No, I need the formal definition, okay? So let me do this formal definition again. It says that the limit as x goes to c of f of x equals L if and only if. So meaning these are equal to each other. Of course, they're not equal. Numbers are only equal, right? So these are logically equivalent. They say the same thing. For every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than x minus c is less than delta, implies the absolute value of f of x minus L is less than epsilon. So this is my formal definition. There's a lot of Greek letters in there. Let me do some translations for us, right? This is for every positive number epsilon just a Greek letter, like me saying pi, right? There exists That's the one I'd have to find. I'd have to find this other positive number, a positive number delta. Such that, I think that might be the last piece that we don't understand that. Such that, what? If my x values are so close to C, right? I'm getting, remember me walking on the curve? I'm getting really, really close to C, but not all the way there. What part of this is saying not all the way there? What part of that is saying I'm not getting all the way to C? I'm walking on the curve and my shadow on the ground is moving towards C, right? Can you visualize that? But I'm never getting to C. What part of this inside of this blue circle is saying I'm never getting to C?
The less than?
Less than, yeah.
The less than, I see a greater than.
Oh.
Greater than what?
0.
Exactly, greater than the 0. Or the 0 is less than the x minus C, right? And so it's saying I can't just plug in C, right? And then what part of it says I'm going left and right? What part of this blue circle here is saying I'm going left and right of?
Or less than the delta?
Almost. Again, I have my chat open if you want to make a guess without saying it out loud. That's fine.
The absolute.
Exactly, the absolute value. The absolute value, right, will be saying in the x direction, left and right, right? So you should see that deltas are related to x values. How do you know that epsilons are related to y values? How do you know that epsilons are related to y values?
F of x.
Exactly. You can see the f of x and the L. Remember, we already said the limit was a y value. So the function is a y value. The L is a y value. So epsilon is giving me some restriction in the y direction, right? Okay. So we'll talk. We saw this on Monday. We saw it again today. You're going to see me apply it today. Okay. You are not responsible for any proofs. I'm not going to ask you to prove things in the class. If you're a math major, you should. If you're a computer science major, you should try and do the proofs. And but I need this to prove a couple of things to you. Okay. Like you may have been told by a teacher in the past that a negative times a negative is positive, but it's no longer just I should just tell you things, I should prove to you. So why is a negative times a negative a positive? Who knows? Isn't that sad?
It's a bit tricky to explain.
No, it's not. It's so easy, but for the longest time we just said, do it because I told you to. But this is over now for us as mathematicians. We want to really understand things as we go forward now. Isn't it sad, right? You've been told things and you don't know why. So a negative, right? A negative is actually translated as the opposite of -3. Right, and and the only things that have opposites are numbers, right? You can see that number line, +3, -3. That's what it means to be an opposite, right? What's the opposite of right?
Left.
I would say wrong. What's the opposite of up?
Negative up.
No, I was thinking of the Pixar movie. What's the opposite of peanut butter? No, it's not. It's not jelly.
Jam.
No, there are no such things as opposites aside from direction or numbers, right? So, so that's why a negative times a negative is a positive. We're just talking about the opposite way on a number line. Anyway, I'll shut up about second grade math and get back onto calculus here. Let's do some limits and see if we can connect a bunch of these, even the formal definition. Okay, so let's just do a direct limit. And these are nice, and this is really my informal definition. Like if I say the limit as x goes to 3 of 5x minus 2, right? The idea here is, well, certainly I can think of, I can see this line, right? So 1, 2, 3, when I get to 3, whatever, I'm at some other height, right? So I can see this height here on the graph, right? So this is a really easy one to do graphically, right? And so what do I get? I get, what, 13? Right, we agree? And so the key here is, if I can plug in. Because remember, I'm just finding the value of a function. So if I can plug into the function, right? So this answer is 13. So graphically, that one's very easy. In fact, do I even need the graph? No, plug in when you can. If you can plug in, you're done, right? So we can look at this numerically as well. So let's do this one. So this one's graphically. Really not. It's just I just plugged in, right? But let's look at it numerically. So I'm going to use my calculator here, and if you have a calculator at home, you can do this at the same time with me. But I'm looking at the limit as x goes to 3 from the left of 5x minus 2, and I'm going to try and predict what I'm going to get there. So I'm kind of building a little table of x and f of x, and I want to approach from the left of 3. So I want to get closer to 3, closer and closer to 3, but less than a number less than 3, and we use like a 2.9, 2.99, 2.999. Once I get to gas station money, once I get to those 3 digits, I should be able to make a prediction, but we'll go one more in case. Right? You with me? So I want you to see me do this on the calculator. Now, when you're taking your test, and if I ever, I just had 2 cups of coffee. If I ever start going too fast, let me know. I can always go back. I can always zoom in. I can always, you can always take a picture. So in my y equal, I want to put that function. What was it? 5x minus 3? No, 5x minus 2. So 5x minus 2. Now on a test, you're allowed to use a TI-83, TI-84, TI-82, any version of TI-84. No TI-89s, no, I forget the other calculator now. So you can always use a calculator on the test, okay? So in my y equal, I put the function. Anybody doing this along with me? I should know if I can go slow, if I can go fast. Nice. Nahom, Soon, and Gerber, thank you. So just make sure if I start going too fast, just stop me. So I got my function in, and then I want to go to second table set. So second table set. So I hit the second button and I hit the window button or the table set button, right? And I want to change my independent to ask. So I'm going to be the one putting in the values, and you already know what values I'm putting in. 2.9, 2.99, 2.999, right? Everybody with me here on the calculator? Nice. So now I go second graph or second table, and you can see I've created an XY table that's blank. And I'm just simply going to put in those numbers. So 2.9, 2.99, 2.999. And you can already see, my 0.9s moving to the right, right? And we know that that's going to converge to 1. So I'm going to get the value of 13 there. I'll do one more, 2.9999. Oh, my calculator can't handle it. So sad. These things, I call them dinosaurs. These calculators are horrible. So you can see once I got to 3 decimal places, I really can see I can predict a 13, which we knew anyway. But this is, again, remember, we're going to be verifying things we do algebraically, right? How are we doing here? So what did I get? I got 12.5. I got 12.95. I got 12.995. I got 12.9995. Right? You can see this decimal piece is moving closer and closer to 1 more, right? And so we get our prediction of 13. The limit as x goes to 3 from the left of 5x minus 2 is 13. And now we do the right? So the limit as x goes to 3 from the right, it's a little bit strange notation first time you see it, but I'm doing x goes to c from the positive side, from the right side. 5x minus 2. We already know the answer is going to be 13, but let's get our table set up. Right? And so our table is going to be 3.1, 3.01, 3.001. I should be able to see 13 at that point, but we'll even go one more. And I'll go back to my calculator, which is all set up for this. How am I doing here? Am I going too fast? We're okay? It's pretty easy so far, isn't it? It gets tough around section 3.6, the chain rule.
That's pretty easy.
Is that good? Good. Lost your camera, Jess. So now 3.1, 3.01, 3.001. You can already see, oops, I missed that 3.0001. You can see that 0.5 moving, right? Right? So I had what, 13.5, 13.05, 13.005. You can see that 5 just running away from the 13, right? That's an unlucky number. And so we can see. So now I got the same height from the left and right, right? The same value from the left and right. I know now the limit as x goes to 3 of f of x is 13. Once I verified left and right. Now, did I have to verify left and right graphically? No, because I can see left and right, right? So numerically, I can't really see it, right? All right, no problem. Let's look at that one with the formal definition. And don't get frightened by this one, okay? Don't get frightened by this. Let's look at the formal here. So we're looking at the limit as x goes to 3 of 5x minus 2 equals 13. Should be equivalent to, or if and only if, for every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of x minus c. But what is c here? Three, yes.
3?
Yep, x minus 3 is less than delta. Implies that the absolute value of f of x, which is 5x minus 2, minus the limit, minus 13, is less than epsilon. So you can see here, as I'm writing this formal definition, I'm putting in the information I know. I know something about c, I know something about f of x, I know something about L. I want to simplify that, right? So for every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus 3, which is less than delta, implies absolute value of 5x minus 15 should be less than epsilon. And so that's the piece I really have to prove ultimately. If I'm proving something like, if I was 10 feet tall, I could dunk a basketball, you'd have to let me be 10 feet tall. If my name was Shrek, then I have a talking donkey as a pet, right? So we assume the first part, and we try and prove the second part, right? So we're going to do this. We're going to let epsilon be bigger than 0, right? So I pick some y value. Remember, epsilons are related to y's. And choose delta equal to epsilon over 5. Now I know, so remember, the definition says every epsilon, there's got to be a delta. And now, because I've been doing this for 20, 30 years, I can see the delta right away that I need, okay? Don't worry, you're not going to be asked something like this. With 0 less than x minus 3 in absolute value is less than delta, we must show, I got to show that I have a donkey that can speak. The absolute value of 5x minus 15 will be less than epsilon. That's the piece I have to prove in order to verify my limit. But I can see, what can I do with that? Does anybody have a mathematical instinct here? Do you see anything I can do here? Begins with an F and ends with a Sidney Poitier. Begins with an F, ends with a Tom Cruise. Begins with an F, ends with an actor.
Factor.
Factor, very good. So I can factor out to 5. That's already positive. I can just factor that out, and I get 5 times the absolute value of x minus 3. But I know something about the absolute value of x minus 3, don't I? I know something about the absolute value of x minus 3. It's got to be less than delta, right? The 5 is still the 5, right? This 5 is still this 5, but the absolute value of x minus 3 is less than delta. Oh, but I picked a value of delta, didn't I? I know that delta is epsilon over 5. Oh, and look what happens to those 5s. They cancel, so I just get my epsilon. And look at what I've finally shown, that epsilon is bigger than f of x minus L. And that's what I wanted. I wanted to show that. Now, when these things are linear, when my functions are linear, it's always this easy. When they're not linear, right, it takes a lot more work. And we'll probably do one Monday like that. So let me try and explain my version of this formal definition, okay? And it took me like several years and a couple of hours in a bar until I finally realized it, playing darts. I was playing darts. And so some of you might not understand a game of darts, but I think all of us can picture the archer, right? The archer shooting at that big white target in the distance, and it's got a center red bullseye. Is everybody with me there? You can picture that's someone shooting the arrow to that white target, right? For me, it's a game of darts, right? And I want to be thinking of so formal definition explained. Just because I explained it doesn't mean you'll get it, but I want you to have the thought, right? I've got for every epsilon greater than 0, that's going to be a dartboard or a target, that big white target out in the distance with a radius of epsilon. Right, the radius of that big target is epsilon, and it's for every size target, right? Right, for every epsilon, for every target I can think of. There exists a delta greater than 0, and that's going to give me the bullseye, right? And that R is delta, so that purple radius is delta. So for every epsilon, for the target with a radius of epsilon, I should be able to find a bullseye with a radius of delta. Such that 0, let me do another color here. 0 is less than the absolute value of x minus c is less than delta. It says I'm going to restrict. You ever see like little kids bowling, and they put up the bumper guards so that the ball won't go in the gutter. It's the same kind of thing. I'm gonna be shooting my arrow, but I'm gonna put up a guard so that my arrow will never move outside of the range of the bullseye to the right or to the left. So I'm saying I'm gonna hit arrows only inside, right? Maybe only inside those green lines. I can't possibly hit outside of the green lines. If I can keep all of those arrows on the dartboard, so make my target, right? Make the target. Find the bullseye, right? Find that perfect hit. Restricting left and right. Hitting the target. If I can do that, I got a limit. All right, now let's think why. Notice my purple marks on my target are all within the circle, all within an epsilon. But remember I said it's for every epsilon. So now what I'm going to do is I'm going to shrink that epsilon down to nothing. And then where does my arrow have to hit? Yes, it has to. In fact, it's even better than the bullseye, isn't it? If I shrink it down to nothing, what becomes of the bullseye?
Nothing.
Yeah. And so what do we call that nothing? A point, right? And that point is L. It's C, L, right? So not only do we hit the bullseye, we hit it at exact center, and we know we have a limit. Now I'll show a dynamic version of that Monday. Okay, I'll show it in my Thursday class tomorrow, and I'll even put that recording up if you want to take a look at it over the weekend. Okay. Again, yes. Question. No.
Is it possible to do another simple example?
Yeah, I'm going to do a not so simple example. Is it going to happen today? Probably not today. Monday. Okay. But I want to do some algebraic limits. So because I'm not testing you on this, let me a little freedom and not doing another example right now. Okay, thank you. I want to take a look at some algebraic limits, and the three algebraic limits. Sorry, Braic. I can spell sometimes. The three algebraic limits I'm going to do are polynomials, and in that case I want to factor rational, and in that case I want to clear interior denominators, or LCD, I'll think about, and radical, and in that case I want to do conjugates. So if you had a demanding pre-cal teacher, you did all of these as difference quotients. So this should be pretty easy for my students that were in my pre-cal class. Right? Nice. So let's do a couple of each of these. We already saw one that was linear, and all I had to do was plug in, right? So, but those are too easy. I won't put them on the test. I'm going to put one of these or two of these on the test. So let's do a polynomial one first. How are we doing here? Are we okay? Anytime if I go to a next page and you're not ready for me, you just tell me. Okay, I can go back. So let's do the limit x goes to 1 of x minus 1 over x squared minus 1. Right, so algebraic limits. I want to think of this function of x minus 1 over x squared minus 1. And first of all, notice what happens when I try and plug in. Remember, I'm just trying to find the height of a function or the value of a function. So I would like to just plug in. That's always my first choice. And in this case, I can't, right? Because when I plug in, I get 1 minus 1 over 1 squared minus 1. I get 0 over 0. This is called the indeterminate form. Okay. And we'll talk a lot about this semester. We know what it means to divide by 0, right? What do we say when we divide by 0?
It's undefined.
Undefined. And undefined actually means what?
Does that exist?
It can be any number.
No, indeterminate is any number. Does not exist, I agree with, but what the hell does that mean? Right? So it turns out when I'm dividing, like 5 divided by 0, I either get positive infinity or I get negative infinity. And I don't know which one, so we say it's undefined. Right? I can't figure out if it's a positive infinity or negative infinity. And yes, infinity doesn't exist. Right? It's a concept. You can't pick it up. So, but when I have an indeterminate form, this one's interesting because sometimes it could be positive infinity. Sometimes it could be 1. Sometimes it could be negative pi. And so it depends on what my numerator is and what my denominator is and how I'm approaching that limit value. So when I get this indeterminate form, I want to come up with a replacement function. Find, so when 0 over 0, we must find a replacement function. Now, if I take this function f of x minus 1 over x squared minus 1, I know that there's a domain of x can't be plus or minus 1, right? Do we agree with that? The domain of f is x cannot equal plus or minus 1, right? That will make my downstairs 0, right? But I can factor this. And when I have polynomial over polynomial, that's my strategy when I'm doing limits. I want to try and factor, right? And so I get a graph of 1 over x plus 1. This is still f, provided I keep the domain. Okay, provided I keep the domain. So meaning f looks like if you remember all the fun you had with graphing rational functions, right? In pre-calc class, there's what f looks like. But at minus 1, it doesn't exist. And at positive 1, there's a hole. At minus 1, the graph doesn't exist at all. And at positive 1, there's a hole in the graph. Again, it doesn't exist at all, but it doesn't exist in a different kind of look. So this is y equals 1 over x plus 1 for x not equal to plus or minus 1. Is everybody comfortable with what I'm saying here? So what I want to do is replace this function with an exact duplicate that fills the hole so that I could find the height. And that function turns out to be g of x with the domain of x does not equal negative 1. So notice right? So what I'm just trying to do is fill that hole, right? So g of x at negative 1, right, has a value at 1. Whenever I get this indeterminate form, this is what I'm trying to do. I'm trying to get a replacement function that will allow me to plug in that value of c. Now, why does this work? Right? Why does this work? We know that for every epsilon, for every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus c, which is less than delta, implying that the absolute value of g of x minus L is less than epsilon. I know g of x is, I can plug into g of x, right? But because I never get to what value of c, what value of c do I never get to?
One.
1. So I can put the f of x in. I can put the f of x in there, and I got my limit. Because I can put the value directly into the function g without 0 over 0, that means I now can find the limit of f of x with this replacement function. So I've done the difficult part, and you can see why I'm saying this part is what's going to be on the test. You're gonna have to realize that you've got a hole in the function where you're going to try and find the limit, and you're going to try and plug the hole. It's called a removable discontinuity for a little bit later, but so we know that the limit as x goes to 1, as x goes to 1 of, what was it, x minus 1 over x squared minus 1 is the limit as x goes to 1 of 1 over x plus 1, which is 1 over 1 plus 1, which is 1 over 2. And there's my limit. So, a couple of things to note. When I get this indeterminate form, you're going to come up with a replacement function, either by factoring, by doing an LCD, by doing conjugates, and then you're going to evaluate the limit. Notice when I evaluate the limit, when I plug in, the limit notation is gone, and then I get the height of that replacement function, which is my limit.
Sorry, but
No problem.
is it okay if you share really quick how you got g of x from f of x really quick?
Yes. Right here. So I had my f of x. I noticed polynomial over polynomial, and I'm thinking factoring, right? So there it is. I factored, and then I canceled, and this is really my replacement function, right? This is my replacement function, and I'm safe with it because x never gets to c, right? Let's do another one, okay? We ready? Sorry, Jesse. The audio's breaking up again. You can try it again or chat it to me. I predicted you were going to say that.
Professor, so what you did is, because it was an indeterminate form, you found the replacement function, and then you plugged into this part.
Yes,
right?
the limits that we're going to do algebraically. Either I can plug them in and get it right away. I'm not going to ask you that, too easy. Still a part of what happens here, right? Or you're going to have to come up with a replacement function. And it's going to happen 3 ways: factoring, LCDs, conjugates, or some combination of them. Okay? And we're going to do a couple more and be done.
And Yeah, and the replacement function is the one you plugged into, right?
Exactly, exactly. The replacement function is safe to plug into. It's obvious what the height is. Nice, Jess, okay? Jesse, okay? Nice. Let's do another. Let's look at a function f of x equals 1 half minus 1 over x all over x minus 2. And let's look at this limit as x goes to 2 of f of x. So if you can see that if I plug in 2 here, I get 0 over 0, right? Right, you're just quickly doing 1 half minus 1 half. Okay, that's 0, and then 2 minus 2. Okay, that's 0. So it's an indeterminate form. So we know we need a replacement function here. On this one, I want to clear interior denominators. So I can really think of this guy as right. I can think of this as fraction minus fraction over fraction minus fraction. And I want to be thinking of the LCD of those interior denominators, not the entire denominator. I'm not going to think of x minus 2 as a denominator. I'm thinking about the denominators of each term in the numerator, denominator of each term of the denominator, right? And so that LCD, or I could just do the product of that, is 2x. Right, so I'm just taking all those highlighted green denominators and multiplying them together. And then, I could reduce if I just found a CD, a common denominator, I can reduce it and I get the LCD. So this one I'm going to multiply through upstairs and not touch it downstairs because there's nothing to clear. I'm trying to clear denominators. Right, so there's nothing to clear downstairs. And I see a couple things cancel here, and I'm rewriting. This is still f of x. Right, how do I know this is still f of x? This is not my replacement yet. What makes you know that this is still the function f of x, not this new function g of x? What do you think?
You haven't factored.
Sure. Better than that is if I plug in 2 at this moment, I'm in trouble again, right? 0 over 0. So now I do notice that I can cancel a factor here, and I get 1 over 2x, and this is my replacement function, right? So all of this is my work on finding it looks like a gun, that's scary. Find a replacement function, right? So I've got it. I know I'm doing now the limit as x goes to 2 of 1 over 2x. And I'm going to plug that in. No more limit notation. I get an answer of 1 over 4. What do you think? Easy?
Yeah.
Is there an easy way for you to look at a function and be like, oh, I'm just gonna add an x over x to this, or I'm gonna add a 2x over 2x to this?
I want to highlight all those interior denominators. So right away I see there's a 1 over 2 and there's a 1 over x. So I need a 2x. It'll always be that simple. You don't have to use the LCD. You could use a common denominator. It'll still work out. You just have to do more work when you factor. Let's do another one, and then we'll maybe... Go ahead. Jesse, what was that? Sorry. The audio is breaking up. I don't know why. I think it was just give me a second. Was it? Give me a minute. So this one would be the LCD, right? But notice there's factoring in it. So when I see just polynomial over polynomial without fractions, right? Without interior fractions, I'm just going to try and factor. If I see fractions inside of fractions, I'm going to try and clear those fractions with an LCD. And now we're going to do one with the radical. We're going to use a conjugate. And then there could be one with a combination of both. Fractions within fractions and a conjugate. And you can all go to my chapter 2 test that I posted today and see the first problem is exactly like one of these, right? It's just going to be on your test too. I don't really change my tests that much. I change the functions. But the concepts you have to be able to do, and I'll just give you different functions. All right, I'll do the next. I'll do the one with the conjugate, okay? You ready? And after we do this one, I only have about 11 minutes left. So I did different functions on the video I just posted this morning, right, on our schedule. I posted for the first class. I posted the other class's lecture. It's 2 hours long, sorry, but you can go look at the limits that I did if you're interested. You could read the book. That's what I'd rather you do. So all these limits start happening in chapter 2.2, right? I want you reading starting with 2.1, secant tangent problem, right? But then you can keep reading 2.2, 2.3, etc. Let's do another limit. This is with a conjugate, okay? So let me write the function. Don't write it. Don't copy it yet. Let me just make sure I like what I'm doing here. Square root of x minus 2, yes, over 4 minus x is x goes to 4. Okay, good. There's my function I want to do. Oops. And obviously I want the limit where there's trouble, right? I want the limit as x goes to 4 of f of x. Question mark. What is it, right? So I quickly try and plug in, because if I can just plug in, I'm done. That will never happen on your test. It will happen in the homework, that you can just plug in, right? So, but if I did plug in, I get square root of 4 minus 2. That's 2 minus 2. That's 0. And downstairs, 4 minus 4 is 0, right? I can do that mentally without writing it. Certainly, if you want to write it, you could. So I need a replacement function, so I'm going to use the conjugate here. My original is square root of x minus 2 over 4 minus x. Multi-terms I want to wrap in parens, and I want to use the conjugate square root of x plus 2 over itself. So look at where the conjugate is, sorry, the radical is, and get that conjugate of that piece. And I'm playing back to 8th grade, 9th grade. A plus b times quantity a minus b is a squared minus b squared, right? The middle terms drop out. And I get my first term squared minus my second term squared, which is what I want, right? I get square root of x squared minus square root 2 squared all over 4 minus x times square root of x plus 2. I'm doing that algebra quickly because I think it should be a review, but you let me know. Again, my chat is open if you don't want to say it out loud. So I get x minus 4 all over 4 minus x times square root of x plus 2. And I notice that I have factors that are opposite of each other. Right, x minus 4 and 4 minus x are opposites. So they're going to cancel to a negative 1. If you want to, you certainly can factor out that negative 1. Right, if you're a little unsure of that. process. You can factor out a -1 either upstairs or downstairs. And notice that those two factors will now cancel. And there's my replacement function. How are we doing here?
Oh, where did you get the negative factor for minus exposure?
So I think you should be okay this line to this line, right? If I just distribute that negative, the 4 becomes negative, the x becomes positive, and that's what I have there. Right? So I think you're okay seeing me undo it. Yeah. So then you just have to now keep that in your memory banks. That you've got to look for those opposite factors sometimes.
Yeah, I see. Thank you.
Good. I'm ready to do my limit now, right? The limit as x goes to 4 of f of x is the same as the limit as x goes to 4 of -1 over square root of x plus 2. That one I can just plug in. So, and once I start to plug in, I'm no longer using my limit notation, right? And I get -1/4.
So, in a way, multiplying by the conjugate is literally kind of the same as multiplying by the common denominator.
Yeah, everything we do is the same. There's nothing new. If you think about really what I'm doing every time is I'm multiplying by 1, right? And this is one of the things we do all the time in calc. The whole calc sequence is we multiply by 1 or we add 0. So we do basically nothing all semester long, just in a very complicated way. Let me do this one numerically once everybody's okay. You're ready for me to move on. Because this is what I would want you to do. I want you to look at the graph, or I'd want you to look at the table and make sure that you're getting the same result, right? So that kind of you can check that page off on the exam, or that question off now, and you know you got it right. It's great to finish an exam and know you have it. You know you're guaranteed a 90, right? It's that one question that you're like, oh my God, did I do that right? I can't think of it. And we'll take all of our tests on Friday, and then we'll take the weekends off, right? If you're keeping up to date, you take your test on Chapter 2 on that Friday, and then we move on to new material on that Monday. So we'll do that 4 times this semester, and then take a final.
So we have a test on Friday, or
Our test will always be on Fridays.
oh, so okay.
It gives me 2 days to grade it and get it back to you on Monday, and it gives you a weekend off.
So that's in general. We don't have no test on Friday.
Tests only on Fridays, except for your final exam, but that would be, I don't know what day that is yet. It's either a Monday or Wednesday during final exam week. All right, let's do this one numerically and then get the hell out of here. I only have 4 minutes, so. And then Moab, you'll stick around for me, and we just talk real quick, okay? And nothing to worry about. I want to go back to my calculator here, and I want to put my function in my calculator. I know at times I can get a little bit fast with this stuff, so don't let me go too fast. If you're following along with me, don't let me go too fast. Stop me, right? Just say, Robert, whoa, slow down, or can you start that over, or whatever. So I'm going to go into my y equal, and I'm going to put in my new function. So, and I've got multi-terms, so I want to wrap them in parens, right? So second square root, where's my square root, of x minus 2, close parenthesis, divided by, open parenthesis, 4 minus x, close parenthesis. So I've got my function in, right? I want to make sure my table set is set to ask. It's pretty good at remembering where you were last time. And then second table, right? And I've got all these old values here in my but I'm just going to overwrite them, right? So remember, where am I getting close to 4? Let me just put in 3.9, right? So 3.9. And remember, I'm trying to get close to a negative 0.25, a negative 1/4, right? And look at that right away. It's right on it. Negative 3.99. 3.999. And look at my calculator at 3.999. I've already got negative 1/4. I don't need to do the other side. If I'm verifying that I got this algebraic limit correctly. If I just ask you to do one numerically, the book will ask you to do them numerically, and you'll get some with a limit and some without a limit. That's why you got to check both sides. But when I'm doing it algebraically, right, that absolute value of x minus c is taken care of left and right. When I'm doing it numerically, I have to take control of that absolute value myself.